The title of this lesson is Pressure in the Atmosphere. This is about the pressure experienced by solid objects when they're surrounded by a gas on a planet. We'll be talking specifically about the Earth's atmosphere in this lesson. So we'll start with our key terms: pressure difference, area, force, and atmospheric pressure. So I'd like you to start by stating the equation that links pressure, force, and area. Now that is the kind of question that you'll see in the exam prior to having to use that equation. And I'd like you to also consider, how does a suction cup stay on the glass? Now, there is a reason I've written that in quotation marks, because the phrase suction cup is an extremely stupid word, and I'll explain why in a moment. So we have a glossary of terms. If you need to remember any of these, please pause the video and write them down. At the very least, pause the video to read through them. Now, the one I will mention here is the word suction. It is not a scientific word. It is a word that's used by the general population, but it's a word for a non-existent force pulling on an object. Suction does not really exist, and in this lesson we'll be explaining why. So, what causes pressure in a gas? So if we have a barrier, which you can see represented by the vertical black line, and you have two different densities of gas on each side, the gas with the greater density, those particles are going to collide with that barrier more often. And each time a particle collides with it, it applies a force to that barrier. So the pressure in a gas is caused by the particles colliding with the walls of a container. Notice there I've accidentally put of a container. Ignore that and just put ER at the end. So pressure difference and density, where there's more particles on one side of the container, the pressure is greater on that side. That's simply because the particles are hitting it more often. You can also have a difference in pressure caused by temperature. So if you've got the same density of gas on both sides, but one of those gases has a higher temperature, that means the particles are moving around faster. And if they're moving faster, that means not only will they collide with the wall more often, they'll also do so with a greater force. So you need to understand from this that the pressure in our atmosphere, the pressure that you feel in our atmosphere, and the pressure that you feel a lack of when you climb up a mountain, is all down to the number of particles that are colliding with you per second. So we have a greater force in this example on the right than we do on the left. And this results in a pressure difference. So here is a graph that we need to understand of atmospheric pressure and altitude. Altitude means how high above the surface of the Earth you are. So if you're at an altitude of 0 kilometers, that means you're at sea level. So you're right next to the coast. You're next to the water. You're at the same height as the water. And at sea level, the atmospheric pressure is roughly 100 kilopascals. However, as you go higher, you notice that the pressure decreases. So by the time you get to about 5 kilometers up, that's kind of the height that you might do a skydive, you'll find that you have a pressure of around, I'm going to say that is probably 46 kilopascals. And as you get higher and higher, the pressure gets lower and lower until you get very, very close to, and then you get to zero pressure. And that's when we have the vacuum of space. You may need to sketch a graph like this in your exam. At the very least, you need to be able to read numbers from this graph. So let's look at the application of this concept. Explain how a suction cup gets stuck to a piece of glass. The wrong answer is the suction causes a force to pull/hold the suction cup to the window. That is wrong. There is no pulling force, there is no suction. The right answer is that the suction cup creates an area of low something inside that is less than something something, AP. The PD results in a F from the atmosphere pushing the cup against the glass. So it's actually the atmosphere that's pushing the cup against the glass. There is no force of suction. That does not exist. So I'd like you to pause this, copy down the question, and write down the correct answer, filling in those blanks from the key terms on the left. Next, explain how you are able to drink through a straw. The wrong answer is that suction causes a force to pull the liquid up the straw and into the mouth. That is not what happens. What actually happens is the mouth creates an area of low inside that is less than the results in a from the atmosphere pushing liquid up the straw. Copy down the question and complete the answer. Explain how a pipette can draw liquid from a bottle. The wrong answer is the suction causes a force to pull the liquid up into the pipette. That doesn't happen. No such thing as suction. The right answer is by squeezing and then releasing the pipette, this creates an area of low inside that is less than the results in a from the atmosphere pushing liquid up into the pipette. Copy the question and complete the answer. Explain what happens to people put out of the airlock in space movies. Wrong answer. The vacuum of space pulls them out. Right answer. The spaceship is kept at a high P inside so that when the airlock is opened, they are pushed out by the F of the A inside the spaceship. Copy the question and complete the answer. So next we have our equation. We've used this one before. Pressure equals force over area. So we can turn this into the definition for pressure. Pressure is the force, normal to a surface, per unit area. So let's do two examples. We want to calculate the force. A suction cup has an area of 0.004 meters squared, placed against the glass, and a pressure in the cavity of 20 kilopascals. Assuming normal atmospheric pressure, calculate the force holding the suction cup to the glass. Step 1. We need to write down what we know. In this case, we have a difference in pressure between atmospheric pressure, which is 100 kilopascals, and the cavity, which is 20 kilopascals. So that gives us a pressure difference, a delta P, of 80,000 pascals. We also have an area of 0.004 meters squared. Step 2 is to write our equation. So the difference in pressure will equal the resultant force divided by the area. So we substitute in our numbers. 80,000 equals F over 0.004. We rearrange to make F the subject of the formula. And that gives us that the force, so the resultant force on that suction cup is 320 newtons. That means if you wanted to remove the suction cup, you would need to pull it with a force of greater than 320 newtons to remove it. Alternatively, you could just find a way to get air into that cavity to normalize the pressure, so that if the pressure on the inside and the pressure on the outside is the same, you no longer require a force to remove it. Next, an idiot in a plane at an altitude of 7.5 kilometers decides to open the door. The cabin inside was being kept at a comfortable 95 kilopascals, but the pressure outside at that altitude is around 35 kilopascals. The idiot has a cross-sectional area parallel with the door of around 0.3 meters squared. Calculate the force with which they are ejected from the plane. Step 1. Write down what we've got. We have 60,000 pascals. That is because on the inside of the plane we have 95,000. On the outside of the plane we have 35,000. And so the difference in pressure is going to be 60,000 pascals. And their cross-sectional area parallel with the door is going to be 0.3 meters squared. Now that's relevant because the wind is only going to blow them in one direction. The wind isn't going to blow both sides of them simultaneously because clearly it's pushing them in one way. So what we look at with this is we look at their cross-sectional area. We don't look at their whole surface area. Next, we write down our equation. Delta P equals the resultant force over the area. We have that 60,000 pascals equals F divided by 0.3 meters squared. We rearrange to make F the subject of the formula. And finally, we get an answer of 18,000 newtons. So they will be pushed out of the plane by a force of 18,000 newtons. For anyone who doesn't know, that's an extremely large number, and it would be very difficult for them not to be pushed out of the plane. And that's the lesson.